Welcome everybody. Today we have a pleasure to host Luna Lima Silva all the way from Niteroi in Brazil. Right. Luna, I would say, is mathematical physicist who specializes in quantum computing, especially like this model of quantum computing based on like scattering of particles through graphs. That was subject of her PhD thesis that she wrote under supervision of Daniel Brod in UFF Niteroi. Yeah, and I guess she'll be telling us all about this subject in her talk. Yeah, in their talk. So the screen is yours, Luna. Thanks for joining us.
Okay, thank you. Thank you for the opportunity. So it's still visible, just to check?
Yeah.
Okay, so I'll be talking about scattering on general graphs. And it will be clear shortly what I mean by this. So I'll start with some motivation, like that we can do quantum processing on graphs. So the main motivation is that scattering on graphs it's a simple model, just the hopping model, if you want to think like that. But it already has encompasses everything that is needed for universality, like quantum computation. All of quantum computation can be explained by scattering on graphs, and it's a less studied area. Actually, only single particle scattering is well known. So we have lots of problems with single particles on graphs that are known to solve some problems. And so my objectives now is to develop a bigger scattering theory on graphs to explain more phenomena. How does it relate to ordinary scattering on free space, on R3, let's say? Which tools are relevant with figures of merit? What can we say in general about scattering on graphs? And I'll present some possible applications of the tools. So just to start, this is actually not a problem of scattering. It's a problem for with quantum walks. But it already shows the power of quantum walks in this case. So this is a problem solved by Childs in 2003, that we have exponentially faster quantum algorithms for some search problem in this kind of graphs. So it's not unstructured search like Grover, but it's this one has proven exponentially separation. So on the left we have some graph. Let me just we have graph. So the problem is you start knowing the name of some vertex and you want to find some other special vertex. So what you can do is the classical way. You just go through each neighbor until you eventually find the exit. But this this becomes a huge problem because we have an exponential number of vertices in this graph. So it's a perfect bifurcating tree. So another way to try to solve this is to make it quantum instead of just a classical random walk. So you have some particles starting here. It diffuses through the graph, and you can prove that the particle has some large probability of being on the vertex you want. So it's because of the structure of the graph that makes it so nice. And actually the quantum particle sees this graph as just one line graph. So it just traverses from entrance to exit in linear time. But this problem actually has another solution with classical algorithm. So if you start walking, if you make a wrong step somewhere and you return to the center vertex, you can correct that error because the center vertex are different from the other ones. So you can just trace back your path and do this until you find the exit. So this is actually a polynomial uh, polynomial sized problem. But if then you just change the problem a little bit, like introducing some random cycle between the center vertices, then the problem is classically untractable. Then you cannot solve it. They prove it that you cannot solve it quickly enough in polynomial time with great big probability. But the quantum walk version still works the same way. The particle diffuses to the graph. It kind of ignores what's happening here, all these random paths, this random cycle here, and you can find exit in polynomial time. So this problem here takes exponential time, necessarily exponential time in for classical algorithms, but for quantum walks, it's polynomial. So that's an example of separation, but this is still a black box problem. So that this is not really a proof of BQP is larger than P, but it's a start. Okay.
So sorry, can I ask on this last point? So it's so here, like you said, it's an oracle problem. So just like the level of access to the graph is via oracles.
Yes.
Okay. Okay. Oh, I see. I see. And then were there some works on like trying to prove that without oracles you do get a separation for some problems like this?
Well, I don't know. I don't think so. The oracle is very important to the quantum algorithm here. It's very
Okay.
ingrained in the quantum process. The way so that the way you solve this problem is that you propose some Hamiltonian based on the oracle on this graph. So I don't know. I don't think there are results that take away the oracle and makes the problem still somewhat easier.
Okay.
Okay, so let us talk about scattering. So it's only a little bit different from what I said before. I actually didn't present the Hamiltonian. What's the exact uh, physical system? So we have two classes of quantum walks. Just to begin, we have coined quantum walk. This is a discrete time evolution. You have a coin space and the position space, and each step you take is you throw the coin, some unitary. Many times it's just the Hadamard coin, and then you shift the position of the particle depending on the state of the coin. Okay, so this is not what I'm going to talk about. I'm studying continuous time quantum walk. So we have some graph. Here I'm just drawing the line graph. And you define a Hamiltonian. So it's very similar to the hopping Hamiltonian there in condensed matter physics. Just you have some hopping terms from one vertex to the next and to the one before, and you define this as a Hamiltonian, and the evolution is given by the Schrödinger equation. So you have just diffusion on the line. So with this, you can make some. You can talk about scattering, just like in ordinary space. So we have free particle states. We say that these are momentum eigenstates. Actually, they are only energy eigenstates. There's no momentum operator on the line, but you could try to define it. They are very similar to the ones on free space, just exponential of the position. But there are some differences. So momentum here is restricted to just a section of 2 pi, because then it would repeat the same states. So that's only because we have this discrete space. And so energy is also different. We have the scattering band has energy only from -2 to 2. So it's a little bit different than scattering on ordinary space.
Sorry, can you say a bit like in technical terms what is scattering band? Yeah.
Yeah, I was just talking about the range of energy that that free particles have on this
Okay.
theory.
Okay.
The particles they do not have energy from 0 to infinity like like a free
Mm-hmm.
particle in real space. They have a
Okay.
different range of energies. Just for people that are very used to scattering theory, there are some fundamental changes. And things are very much similar when we take one other step. So we want to study scattering on graphs in general, not just on the line. So the structure is as follows. So we have some graph that I don't know, maybe it processes information in some way. It encodes some problem in some way. So that is scattering center. The particle comes here and scatters on this graph. And the particle is free on these rails, these lines here. So I want to study what are the amplitudes of some particle coming through some specific rail, scattering on the graph, and then coming out on another specific rail in superposition generally. So I want to know these kinds of amplitudes.
So, can I ask a question?
Of course.
Sure.
I mean, when I just, I mean, at first glance, the philosophy of this graph actually theory you present is very similar to the Feynman diagram, like when you consider the propagator between 2 points. So you consider the graph theories have the same philosophy as scattering process in the quantum field theory.
Sorry if I didn't get it. So if I process the graph scattering the same way as
So when we can describe scattering process in the quantum field theory using the Feynman diagram. They also use propagator, and this all like you can split. You can actually have a Feynman graph as element of a scattering process. So when from one point to another point, you will have a propagator, and but this so it sounds like actually graph theory is similar to the representation of a Feynman diagram. So and even not actually necessarily actually Feynman path integral, even in ordinary quantum mechanics, you can also describe such graph. Before, I just wonder if your philosophy is the same as the traditional physics diagram.
So I actually the way that we're going that I solved this problem of finding this scattering amplitude it's using Lippmann-Schwinger formalism. So it's I don't know, I'm not very familiar with using Feynman diagrams to describe scattering. So
but the name Schwinger probably like it's associated to quantum field theory as well, right? So
yeah.
maybe the techniques.
Actually, Schwinger actually dislike Feynman path integral, Feynman active diagram, but he uses Feynman diagram kind of informal way. But they are actually representing same thing, but he just simply hates actually Feynman diagram.
Okay, so let's say maybe we can continue the discussion like after about the relation to the quantum field theory after until like after the talk. if that's okay, Typhon. Yes.
Sorry for take your time.
No worries,
That's
no worries.
okay.
Yeah. For sure, there are some similarities when you consider scattering process. Okay.
Yeah, of course. So, okay. And so we have scattering eigenstates. They represent this situation. And also we have similar to scattering in free space, we have bound states. So we have two different kinds of bound states. We have evanescent bound states that the amplitudes decay exponentially away from the scattering center. We have confined bound states. They have a little bit different properties than the usual bound states because they lie on the same range of energy as scattering states. So they behave a little bit differently. And this is actually new. This is different from normal scattering theory because there is no potential here. There's no second particle that makes some potential for the incoming particle that makes it stuck to the graph. So this is actually just like free space, but the particles can get stuck in this different space inside the graph. So this will be this will appear later. So single particle scattering, just to gloss over some definition. So we parameterize the vertices in some specific way, and we can describe the eigenstates. So they have the eigenstate of momentum P incoming on rail N. So this plus sign is just that it is incoming and not outgoing. So we have two different kinds of eigenstates. The particle is incoming through rail N, and it scatters through each other rail M with different amplitudes. So this here is the scattering matrix that tells me what's happening. And also we have to say we have the amplitudes inside the graph, inside this vertex, this different space. And this problem is solved for single particles. It's just linear algebra. So the S matrix and the psi matrix are known. This is the other thing I was saying, the outgoing basis. So it's a different basis of eigenstates. So instead of having a minus sign here, meaning they are incoming, they're decreasing in vertex number, we have a plus sign here. So this is different also from ordinary scattering because going in one direction is not the same as incoming on the same direction. Like on a line, a particle going with momentum to the right is the same, just time reversed of a particle going to the left. Here it's different. It's a little bit different because of the asymmetry of space. There's no translation invariance. And I'll briefly review the work of Childs, Gossett, and Webb, that we can do universal computation. So how can we make the gates? How can we make this translation? So we just represent everything in dual rail. So this is a qubit that can have state 0 or 1. And if I want to do some quantum unitary, it can be represented by the scattering on some graph. The only thing that we need is that particles that come from the left, they still go to the right. They don't reflect back. Then it would be a problem. So if I have one particle going from left to right, it scatters on the graph, and then it has different amplitudes from continuing up or down, then we effectively have implemented some unitary. So we just need to look for graphs that have perfect transmission. So the scattering matrix only takes in states to the states on the left, the scattering through the left, to scattering on the right. So they have this block diagonal form. And let us get away with those infinite rails here. Just put some white dots to represent where they are the connecting points. And we can implement every a set of universal gates. So this gate here is just a phase gate. So a particle, if it's coming through rail 1 or rail 0, they have a different in phase. This one is a base changing gate, just like the Hadamard gate. So a particle incoming through 1 will come out in a superposition of 0 and 1. And this is for a specific momentum. So for a different momentum, maybe the Hadamard gate looks very different. So just to say some, just to say it, get it out of the way for now. So this is already a universal set for single qubit gates, the first two. And in their construction, they wanted to find, we need just one more entangling gate to have universality. So they are looking to implement this one gate, a C-phase gate. And the idea to implement this gate is to make the particles meet. They have to interact. They have to interact when they are both on the one rail, the 1-1 state. So one way to do this is make them meet physically. The physical qubits, the physical particles have to meet. And if they travel on a long line, then the only thing that can happen is that momentum is conserved and they have some global phase. And they acquire some global phase because of invariance of translation. So we have momentum conservation and energy conservation. Then the out state is the same as the in state. And how you make this into computation, how to transform this into a gate, because the particles are not traveling from left to right, you have to make some very big construction to make it happen. So here, if the particles are in any
sorry,
combination.
Can I have a question, Luna? Technical
Yes.
question. Can you move back? So I understand that when you describe scattering of a single particle in a graph, like basically everything was it was just Hamiltonian evolution, and the Hamiltonian was basically adjacency matrix, if I understand, of a graph, right?
Yes.
Do I understand it?
Yes.
So now when you have two particles, how do you define the interaction? Because you could just, I know, pretend that they don't interact at all, and it's a well-defined, let's say, it's a well-defined dynamics. Just nothing will happen, nothing interesting will happen. So how you extend the model of interactions?
Yeah, they both have single particle Hamiltonians at the adjacency matrix.
Yes.
And you can consider actually almost any interaction between the particles that is translation invariant. So you can consider maybe a Bose-Hubbard Hamiltonian for the particles. If they are both on the same side, then they have an energy penalty.
Okay.
But this is very general. Any two particle interaction will be enough to
Okay, I understand. So you just your constraints are that you consider those sort of scattering states as your sort of you build your logical encoding from those scattering states that sort of like which allow you to infer that only the phase will change, basically.
Yes.
If I understand. Yeah. Okay.
Yeah, they actually really consider the Bose-Hubbard interaction, and they show that this angle can be made to be pi over 2. So this is a C-phase gate. It can be used to as a two qubit entangling gate. But yes, for now, any interaction would be good. And then this is a C-phase gate. So how do you read it? If the particles, so we have the qubit W and the qubit M. So in their paper, they have different roles in the computation, but it's okay. Let's make it simple. If they are both on the 0-0 state, then they remain on the 0-0 state. If they are if one of the particles is in the one state, you have some kind of contraption here, a gadget, that makes the particle travel on this specific line, and it goes back to the encoding. And one thing happens only, the particle meets only if they are both in the one state. And then they meet on this long line, they acquire relative phase, and they come back to encoding. So that's a really sophisticated way to implement a C-phase gate. And so that's the thing that I wanted to improve. So that's the question that I had. Can we make a C-phase gate more easier? Like we have to consider very, very long paths for the translation invariance to be well approximated here. And this seems like it's not very easy to make this construction. It's very, very complicated. Lots of parts. And actually, just to tell a little bit of what's happening here, how can a graph make a particle only traverse to a specific path? This gadget, this is a momentum switch, so it's another paper by Childs. It's a graph that takes a particle with specific momenta and makes it go through rail 1 to rail 3 and 3 to 1 also. So a particle comes here and only exits through 3. So in this drawing here, it comes through the left and goes down. And if the particle has a different momenta, then it traverses along the other edge, the dotted line here. If it has momentum pi over 2, then it goes from 1 to 2. Well, actually, I should have drawn this differently, but you get the idea. One particle goes from 1 to 3, the other particle goes from 1 to 2. And that's enough for the construction. So this kind of gadget is the thing that we can make it better by improving the theory, by considering more particles. So that's what I'm going to explain. So here, now I'm going to talk a little bit about formal scattering theory, because that's needed to talk about two-particle scattering. So just to talk about this very quickly. So we want to consider asymptotically free particles. So these limits, they have to exist. So if you want to consider some incoming state to the graph, so this is like a free particle on the line before it encounters the graph, it has to correspond to some real scattering state. And this is not always the case. So depending on the theory, on the Hamiltonian, having this condition satisfied is what we call the asymptotic condition. So can we use every possible state of the Hilbert space as a trajectory? And this is not always true. So we have to deal with some spectral theory here. So for these Molar operators to be defined.
Sorry, I got maybe distracted for a moment. Can you elaborate again about those asymptotically free conditions?
Yeah. So basically, we want to say that we can prepare any state, any incoming state, and it will be explained by scattering theory. So that you can define the S matrix. So some things.
What is U0 and what is U0 of t and U of t?
So U0 is just evolution without interaction, without the interaction between the two particles that I want to consider, and U is the actual interaction. So the free particles, the free particles when they are away from each other, they must be explained by there must be a scattering state that takes into account the interaction that corresponds in the asymptotically distant past and the future. So
okay,
I want to
say that So for every psi in, there should exist psi with that property.
Yes.
And the same for psi out.
Yes. That's just
okay.
Just to say, if you throw a particle into the graph, it will come out of the graph. They will not be stuck in some subspace, inaccessible from the outside. So basically, that's the definition of the Moller operators. So if these limits make sense, they define these operators. And we have to, the solution is that we have to restrict to the absolutely continuous eigenspace of the Hamiltonian. The eigenspace of scattering particles, of free particles in this case. And so this is the definition. So that's how we construct the S matrix, what explains all the scattering. And the Moller operators will be complete. So that's equivalent to saying that the S matrix is unitary. We want to find the particles after scattering. And this will happen if, so we are guaranteed by the Kato-Rosenblum theorem that this will happen if the interaction is trace class. So if the interaction happens only inside the graph, then it's a finite interaction. Then it's trace class, then everything works nicely, and the scattering theory will be nice. But one price that we pay is that we have to only consider scattering states on the absolutely continuous subspace. What do I mean by this? Is this kind of subspaces. So we can explain, if we want to talk about two particle scattering, we can explain scattering with two free particles incoming to the graph, or even with one bound particle to the graph. We can consider this as a free state, because in the distant past and distant future, these particles don't interact. They are not both inside the graph. So we have to take out of the Hilbert space the possibility of having both particles inside the graph. So that's the one conclusion from this detour on spectral theory. So one thing that's never going to happen is two particles coming inside the graph and both are stuck to the graph. This does not happen, as we will see. So these are the asymptotically free states. They are free in the sense that they are not meeting each other, but some may be bound to the graph alone. And, well, as I was saying, I want to study scattering with more particles at the same time. And the Hamiltonian that I will consider, maybe I don't know if it's visible, all the colors, is in green and blue, the single particle Hamiltonian for both particles, so they can hopping through the edges. And we consider some specific interaction. Here's the Bose-Hubbard interaction. If they are both on the same site, they have some energy penalty, represented by red here, only inside the graph. So to make sure that the theorem holds. And so that's the same slide. And if we make this separation, the Hamiltonian that we already know how to solve for, the Hamiltonian on the rails and the graph. So this is the single particle Hamiltonian. If we separate it, the interaction-free Hamiltonian and the interaction that we called V, we can solve it with Lippmann-Schwinger. So I don't know if everyone is familiarized with Lippmann-Schwinger from scattering theory. This basically is equivalent to the Schrödinger equation, but it takes advantage of knowing the structure of the single particle eigenstates. So we can input here in our equation the single particle states, the free single particle states, and the output here on the left with a plus sign is the actually scattering state. It encompasses everything that happens in scattering. And the main result from my thesis is that we can describe explicitly the S matrix. So what's the probability of starting out with some set of incoming particles or even bound particles? So these are the initial states. What's the probability of having some incoming particles to some outgoing particles? So we have just the normal probability, the normal amplitudes, as if there were no interaction, and then there's this whole interaction term. So this is a little bit different from single particle scattering, because now the particles can exchange energy. In the single particle case, the particles they go inside the graph, then go out with the same energy. They don't have anywhere to change its energy. But with two particles, they can become spectrally entangled. They can change any amount of energy, and that's a little bit complicated to deal with. But we will say some things about it. And that's the only thing that was not defined before. This C matrix here is just a submatrix of the Green operator. So we have this inverse of the Hamiltonian here. And we will take only a submatrix. Only it depends on the interaction. So because of the Bose-Hubbard interaction, we take this specific submatrix here. So that's all we have to do. Just more linear algebra to solve this problem. But now it becomes a more sophisticated. And
sorry, can I ask, like, because I mean, even in the single particle scattering, is it clear how like properties of the graph affect scattering? Because I would expect, yeah, some properties of the graph would decide what's happening, right?
Decide.
What do you mean? And one question: what is G0 in the sum also?
It's the inside of the graphs. These are the vertices inside the graph where the interaction takes place. So for single particles, we have everything, all the information. So the scattering of single particles is well known. We actually don't know if I don't know if we stitch some edges together, if we make changes to the graph. It's difficult to see what does change, how does it change the scattering amplitudes, but we can do this calculation. It's just linear algebra.
Okay.
But for two particles, it's the same. We can make the graph and look at the scattering amplitudes, but it's very difficult to say like, we want to make a C-phase gate. How do we do that with one graph? This inverse question is still difficult.
Right, and I guess this spectral entanglement is a problem, right? Because you need to consider possible like scattering through your encoding should somehow take this into account.
Yes. But we can find some graphs where this spectral entanglement is not important. So that's one thing we can do. That's actually what Andrew Childs did in his construction. He made a big graph, and he made sure that the particles would conserve their energy. So he somehow solved the problem of spectral entanglement. And let's look at some examples. Let's look first at, on the line. That's the first example we had. So let us say that we want to look at the interaction of particles on a line. So that's where we took the C-phase gate from before. And let me see if I really want to. I think I had. Yeah. Okay, let me talk about it. And actually, just to briefly say something about this, we can solve the problem on the line. The problem that before we had translation invariance, we can look at it from the perspective of finitely many vertices, because it's a problem. If that picture that I show of the C-phase gate, it needs to have some finite number of vertices. You can't consider an infinitely long line vertex. So we can solve this problem exactly in using the things that I showed before, the scattering matrix. So just consider here interaction on these maybe 5 vertices and make this go to infinity. So this problem can be solved quite easily using approximations. So that T matrix is actually a toplets matrix. It has some nice symmetries. We can approximate it to a circulant matrix that has even more nice properties. we have a way to transform from one type to the other. And that T matrix is just this T matrix here that we have to take the inverse. And we can prove that in the limit, in the asymptotic limit, where we have an infinite, really infinite line, that the S matrix is really just a phase. So there's no more spectral entanglement. And this is the phase acquired that theta that appeared before. We have momentum conservation, but we have pointwise convergence. So that's going to be explained in the next graphs when we talk about the line graph.
Like when you say pointwise, okay, you would explain what you mean by this.
It's just that this is the scattering matrix on the asymptotic limit, but not every state will behave nicely on this transformation. So the problem is, if you consider a wave packet with large or small width, so depending on how you prepare your real wave packets. So we have these numerical results here. So on the line, scattering on the line, we are trying to use so this fidelity here. This graph is fidelity against the size of the wave packet. So we have the line. We are trying to make a C-phase. We are trying to compare it with a C-phase gate. So the particles are scattering from left to right and right to left, and they acquire a phase. So they should acquire a phase. So this is the fidelity of what's happening of the scattering matrix with just having acquired a phase. So you can see that if the particles are almost perfectly localized in momentum space, so this is width in momentum space. If they have specific momentum, then the fidelity is low. So this is the fidelity with that C-phase gate. Here, 70% is the minimum that you can. Is the fidelity between the C-phase gate and nothing happens in the identity. When the particles have very sharp momentum, they have peaking momentum wave packets, then they will not even see each other. With just a finite number of vertices, the particles will be very spaced out in position space. They will not meet. So that's the problem of pointwise convergence. But if you choose some little larger wave packet, then you can show that the fidelity goes up with the number of vertices. So the longer the line, the better it is to make a C-phase gate. So we have here only 27 vertices. It goes already to over 95%, but the trend is nice. So now I'm plotting the distance of this optimal point here to 100%. So this infidelity here goes to 0 in a polynomial way.
So Luna, can I ask? So this infidelity, is it because you go outside of the encoding?
Yes, exactly.
Or because if you stayed in the encoding, it shouldn't be much of the problem. That will be some other gate, maybe different phase or something like this, right?
Yes.
So
Yeah, what
So the
this distance
infidelity is
here,
because you are outside of the encoding.
yeah, outside of the encoding and outside of the range of the what the C-phase gate should do. Is both things. So this distance here,
Okay.
this 5% is because the particles did something you didn't want them to do. They got outside of encoding, or they implemented a different gate that you didn't want it.
I see, but then can you shift your perspective and say, well, actually, okay, maybe I wanted to do C phase, but I'm implementing some other 2-qubit gate, which is still universal, and you're still like how to phrase it? Your fidelity just increases then, because you maybe like
you can think like that. You can calculate the fidelity. This is the fidelity with the C phase gate with the phase that we expected. But you can calculate the fidelity to that it had performed some specific 2-qubit gate. And you can look at the best fidelity, the best gate that it approached. That's another way of thinking about it. So okay, that's for the line graph. So that's my results applied to the line graph. So we can show exactly how fast the line graph it implements a good C-phase gate. So, and this is analogous to optical systems, to a paper by Broad and Combs, where they implement a C-phase gate using cross-kernel nonlinearities, and the setting is almost exactly the same. So you have some quantum dots here, some atoms where the photons can interact, and they show that the photons using this interaction, they actually perform a nice C-phase gate with few sites, with few quantum dots. So this is almost the same. It's very similar. And to look at scattering in general graphs. So we for general graphs, we don't have that approximation that we had before. So this interaction term, let us call it just R. So this encompasses everything about the interaction between the two particles. And let us study this quantity here. So this is the scattering amplitude from in state to out state. So the two particles are coming in and then coming out. And we can study it for the line still. And we can see that we can observe momentum conservation in these cases. So again, I'm plotting these scattering amplitudes from in state to out state. So the particles begin with momentum pi/4 and pi/2. Here they are going in the same direction. Here they are going into different directions. So remember that this contributes to the S matrix multiplied by a delta of energy, conservation of energy. So the only amplitudes that matter, the on-shell amplitudes, are the amplitudes on top of this conservation of energy, this solid line. And the dashed line is the initial momentum. So that's minus pi/4, that's pi/2. And you can see that the out state, where we have big amplitudes, is exactly on the line that is K1 plus K2 is constant. So momentum is conserved on this blue line here. So when you consider more and more vertices on the line, so you have this graph becoming even more defined here. So we can look at the graph of this function here and see what is happening. We can look at different geometries of graphs and see that if we can resolve the spectral entanglement. So this is basically eliminating the spectral entanglement in some limit. So we have a different graph now. So now this is new. Consider that the particles can income through the left or through the right, and they encounter this tower of vertices. This is actually analogous to another optical system considered in this paper, where you have optical cavities and a quantum dot on the final level here. So we just translated it to graph, and we wanted to see what we get from this, because they are trying to make a C-phase gate, so they supposedly solve the problem of spectral entanglement. And it has another nice property that it approximates translation invariance. So it's still a big line. And what we have in this case, so again, the same graphs as before. We consider some incoming particles with specific momenta, pi over 4, pi over 2. This is still the energy conservation. And you can see that there are the amplitudes, the scattering amplitudes with most absolute value still lie on this line here. It's not conservation of momentum, but they do meet up exactly at the same point. So the out momentums are the same as the in momentums. So the in momentums are pi over 4 and pi over 2, and the out momentums with big scattering amplitudes are the same. So something is happening in this graph, on the geometry in this graph, that makes it good for eliminating spectral entanglement, just as in the optical system. But this is kind of different mechanism. The graph is very different from the one that I showed before. Okay, and now to look at some different other applications. So up to now, we considered two traveling particles, but now I want to consider how does a bound particle to the graph changes the scattering of another particle coming to the graph. So how does a bound particle can change single particle scattering? So you have one particle and a second particle in a traveling state. So what is the probability, what are the amplitudes of scattering? So these T amplitudes here are just the single particle scattering, and it is changed by interaction. So this R is proportional to the interaction. So the particle can still scatter as usual, but other things can happen. So the particle can scatter without changing the energy of the bound state, or the bound state can change its energy. So the traveling particle can excite the bound state or make it lower its energy, or it can even eject the particle. So in pictures, we have elastic transmission. The particle just bounces off without losing energy, or it can bounce off changing its energy, or it can take the bound particle and eject it out of the graph. So what I said before in formal scattering theory is that you cannot have a process with both particles stuck to the graph. That's why it didn't appear here. So we can study these lots of different scattering processes. And we have no imprisonment of the incident particle. And let us look at some nice examples of where that's interesting. So let us consider this specific graph here. So I'm plotting here the transmission probability and reflection probability of a single particle, no interaction. So depending on the energy of the particle that is between 2 and -2, it can perfectly transmit or perfectly reflect. So that's the whole story for a single particle. But let us introduce to this graph a second particle in a bound state. So we have 3 different possibilities. They're evanescent and confined bound states. Let us try each one, look at what happens. So let us include in the graph the evanescent bound states. There are two evanescent with different energies. So dash in the dashed line is the same coefficients as before, as I showed before, the single particle ones. And what happens is that the scattering of the second particle becomes very different. So where not in the presence of the bound particle, the particle would perfectly reflect, not transmit. Now in the presence of this bound particle with positive energy, it now almost perfectly transmits. And maybe another interesting feature of this graph is in the presence of this evanescent bound state, for almost all energies, the particle will not transmit on the graph, only if it has high energy. And it depends on the specific bound state. So if it's the other bound state with lower energy, then it only transmits for low energy traveling states. And the graph becomes opaque for different incoming energies. So it behaves as a momentum filter. So, or energy filter. If you have low energy, you don't transmit. If you have high energy, if the particle has high energy, then it can traverse the graph. Depending on the particle that is already there. So it's a conditional momentum filter. So that may be interesting. So another thing that's interesting, if you then include the confined bound state, and here I'm drawing the transmission probability. This is for single particles. Depending on the energy, the particle can transmit or not. But then if you introduce the confined bound state, then the graph becomes transparent, perfectly transparent for all energies. So again, you can use it as some kind of transistor. If you put a confined bound state on the graph, then it's perfectly transparent. Then if there is not the presence of the bound state, then it can scatter with a different profile. It can perfectly reflect if you want, if you are on this specific energy here. So all of this all this computation were done numerically with that S matrix that I showed before. And there's still another feature that we found. So let us look at the different graph. So again, the particles, they can come in from left to right if you want. And they scatter on the cycle, this big cycle. This is the single particle transmission and reflection probabilities, depending on the initial momentum. But there are a lot of confined bound states. And what will happen if we include a confined bound state here? How will it behave? So what happens is if you include some specific bound state, so we have 4 different bound states with 4 different energies. Here I'm considering scattering with initializing this confined bound state with the highest energy, just for example. And what happens is if you throw a second particle to the graph, then depending on its energy, the bound state will change, the bound particle will change its state with some different probabilities. So it will happen some inelastic reflection. So the bound state that was initialized in this high energy, they have some amplitudes of changing to the other bound state. So we can use this as control. So if you have the particle in this chi2 plus state, and you throw a particle with energy around here, the bound particle will change to the state chi1 plus. So that's controllable, depending only on the energy of the scattering state. And maybe that can be used as a different paradigm. Maybe you can use the bound states to encode the qubits. So I have here a qubit with four different states. QDIT, and we can control it with a different with an external particle. So maybe we can do quantum computation with those bound states. So these two things, right? We can use it to encode information, and we can control it. And okay, so this is all new information deriving from the scattering matrix and all the things that I did on my thesis. And now I'm just finishing.
Hey Luna, so just like if you could try to like wrap up in 5 minutes or so, that would be great. Yeah, sorry,
Yeah, sure.
but it's very interesting. Just we can discuss, in questions. Yeah.
Yeah, I'm just finishing. That's okay. So what we can take from all of this, we can quantify scattering with more than one particle. So we talked about nonlinear scattering in the presence of bound particles. We got processes analogous to excitation, ionization, these other processes in usual scattering theory. We can study different graph geometries in a more broad sense by looking at the off-shell values of the scattering amplitude. And actually, I didn't show it here, but we can talk about cross-sections as in usual scattering theory. Is another way to study different graphs in this context. And some questions that we may answer is maybe coming back to the beginning of the presentation. Can we use this to make a C-phase gate more directly with a low number of vertices? Can we make it more efficient? And maybe we can use this theory to study restricted quantum walk models. Maybe if the particles do not interact, can we prove that it has maybe the same complexity as boson sampling? Or maybe if we use just particles with a specific momenta, does this become not universal in some way? So that's an interesting way to use this theory. Of course, there are some graph theoretical questions. Maybe we want to study heating times and mixing times for two particles. These quantities are very useful to devise different different how do you say it? Different ways of solving problems, different algorithms in graph theory, and maybe use these theories to some applications, like the tight binding model. It's the exact same Hamiltonian that we consider. So maybe we can study electron transport in different lattices, in more general lattices. So that's one nice application. And this is as we've seen before, this is a toy model for forums in quantum dot network. So we had similar results to two different optical systems. Maybe we can, if we want to find some properties, optical properties of photons interacting with quantum dots, maybe we can look at the graph theoretical version of it first, and then do the more difficult calculations in the optical systems. And that's it.
Thank you, Luna, for a very nice talk. And sharing with us like contents of your like PhD, and I think those are very nice results. Right, so we have now some time for questions or comments from the audience. Taehoon, you wanted to ask?
Yes. So when you also include the bound state, but in that case, you cannot assume the asymptotic free condition, right?
Yes, exactly. We have to prove it that it is satisfied.
Satisfied?
Yes, because
but when the bound state, when you consider the bound state, as time goes infinity, you don't have free state.
Yeah, because it's free state in the sense that, in the sense of the interaction. So the particles are free if they don't interact with each other, in that sense. So looking at this limit, maybe.
In bound state?
Yes, if one particle is bound to the graph, is stuck to the middle, and the other particle just is traveling outside, then the interaction becomes negligible, and you can consider them free.
But this condition is for just one of a particle or all the particle?
So this condition is satisfied in the absolutely continuous subspace here. So it's when I show you this subspace comprised of traveling particles or one particle bound and one traveling, then this is the space where the scattering, the asymptotic condition makes sense. So I'm not considering bound states of both particles on the graph. Two particle bound states. These are forbidden. These are not.
You use only partial asymptotic free state as a condition. Not every particle is completely free in the end.
Yes.
I see. Thank you.
Some other questions to Luna? Right. Maybe I have one general question. So in the interaction, if I understood well, you assume Hubbard model, right? Mm-hmm. So like the particles interact like if they are on site, right? Mm-hmm.
Yes.
Okay, and you assume that interactions happen in the graph itself. So how sensitive is are those results to details of this interaction? Like, do you think it would be like if you had, some other forms of interactions? I don't know. Would it drastically change the picture?
So I don't think it will drastically change. So this process of finding the S matrix is very general. So all the details of the interaction is on this T matrix here. This this green operator. So if you consider a different interaction, so the Bose-Hubbard interaction is appearing here as this U times the particles on the same side. This will only change the submatrix of the green operator that you have to consider. So
okay.
So it will be still easy. We have the same difficulty with different interactions, but one drawback is that we have to consider a trace class interaction for it to work. Actually, the way that I solved it, we had to consider interactions on a finite region. And that's seems to be okay to consider only interaction on this finite region, because if you want to do quantum computation, then the particles should not be on the same rail at some time, or it should have low amplitudes for that to happen.
Okay, so one further question: how difficult would it be to extend it to free particle scattering? Does it become a nightmare, or
adding one more particle? It would become maybe just a linear algebra nightmare. It wouldn't be hard. I think this result was most as to show that it was possible. So I think that for more particles, the maps would be the same complexity, but the computation would be a little bit more harsh.
Okay, nice. Okay, are there any other questions to Luna from the audience or organizers, or Okay. If no, I guess we can. Okay, okay. I can just comment that those are like pretty nice results, and I hope you would like pursue some of those things, later. Because Wojtek, you wanted to ask or not? No, or you
I just unmute myself, but I don't want
Okay,
to ask.
okay. Right. So thanks again, Luna, for a very nice talk. I think that was pretty, yeah, like nice exposition of what you did.
Okay, thank you for the opportunity
thanks.
again and for listening to me. I'm sorry that I rushed a little bit, but that's a big presentation.
I think that was nicely balanced. So, yeah. Okay. So yeah, thank you everybody for attending, and bye.